Recalling some ideas from section 6.1, two angles are complementary if those angles add up to 90 degrees and supplementary if their angles add up to 180 degrees. So we might see those terms again in this section, complementary and supplementary. Now topic 2, trigonometric functions of angles or rotations. So up to this point, we've defined the 6 trigonometric functions in terms of acute angles. Not all angles are acute. There are coterminal angles that are not acute, but happen to represent the same terminal side. So we're going to expand our definition of those 6 trigonometric functions to any angle or rotation. And it matters where the rotation ends. That's all that matters, where our rotation ends. That's our terminal side. So we should get the same trigonometric ratio for any terminal side. Okay, so we're going to construct reference triangles based on any standard angle, and we're going to define our 6 trigonometric functions based off of those. All right, so we have this circle kind of drawn right here to show that as I rotate an angle, it doesn't matter how big the triangle was, right? We're just going to be rotating it around this arc. If I rotate it once or twice, like I can rotate this one all the way around again, around the circle again, to get to the same angle, it's going to have the same trigonometric ratio. So we define this based on this circle pattern right here, and we define this triangle to be x, y, where this point right here has coordinates x, comma, y, and then r is the radius of that circle, because that's how the Pythagorean theorem is written. It's x squared plus y squared equals r squared, and that's the radius of the circle. They're very similar. Okay, and so the trigonometric ratios for these would be, for this angle, I would have it's an acute angle, so it's the exact same as the regular 6 trigonometric ratios, just the sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent, etc. Now, that's normal because this is already acute. The original theta right there is already acute, so it doesn't change anything. But what about if the theta is obtuse? Okay, if the theta is obtuse, there is still a reference triangle. It's just the reference triangle isn't in quadrant 1 anymore, but I still have an xy definition based on that ordered pair, and I still have r with the same definition. And so that's going to allow me to compute the sine, cosine, tangent in terms of an ordered pair, x, y, and a radius r. All right. So the sine, no matter if it's an acute angle or an obtuse angle, the sine of that angle, because that, look at this acute one as well at first, the angle is going to be, first of all, hold on, I've got sine, so that's y. Sine is y over r, and cosine is x over r, and then tangent is y over x. Okay, I want to see how this plays out in the next one with the reference triangle. The reference triangle has something different inside. It has this angle right here inside. So if I was doing the sine of that angle, I just want to be sure that it would be the same or similar to the sine of the other angle. So if I reflect this angle over here, then it would be the same triangle with the same x and y. The only difference is that this x is a negative value. So if I use the full angle, it's the same ratio, the same x and y are in the same position. So I'm still using for sine y over r. I'm still using for cosine x over r. And then for cosecant, cotangent, and cosecant, we're just going to flip these around. So it's going to be r over y, r over x, and x over y. Okay? Now, r is always positive because it's a radius value. But x and y can be positive or negative, depending on which quadrant you're in. Okay? So that's the difference between when I have the obtuse angle, is I have to consider quadrants and positives or negatives. Okay? In quadrant 1, they're all positive. X's are positive, Y's are positive, R's certainly always positive, so they're all positive. In quadrant 2, the X's are negative, and the Y's are positive. Okay? So if the X's are negative, anything that uses X like cosine and tangent, will be negative because those use x. And sine, which doesn't use x, it uses y, which is positive, is going to stay positive. In quadrant 3, you have negative x values, negative y values. So anything that uses x and y once will be negative, but tangent, which uses both of them, is going to be double negative and therefore positive. So tangent's going to be positive, sine and cosine are both going to be negative. And then in quadrant 4, you have positive x's, negative y's. The x's are positive, so that means that the cosine is going to be positive. But since y is negative, anything that has a y and a positive, so a y and an r or a y and an x, will be negative. So we'll have negative sines and negative tans. Okay. Now, to remember which ones are positive and which ones are negative, besides just computing them, sometimes we remember that all are positive, sine is positive, tangent's positive, cotangent is positive. So the mnemonic device is all students take calculus, or all pre-calc students take calculus, ASTC, all students take calculus going from quadrant 1, 2, 3, 4. All students take calculus, all are positive, sine is positive, tangent's positive, cosine is positive. So make sure you take calculus. Alright, and then taking a look at example 2, find the 6 trigonometric function values for the following angle. So beta, I don't know what beta is. I don't know what the angle itself is, but I don't need it if I know x and y, because that gives me all the values I need for my trigonometric ratios. So the x value is negative 12, that's the base of my triangle. The y value is 5, that's the height of my triangle. The first thing I need to calculate is r, because for sine and cosine, I need to know the hypotenuse. So we're going to calculate r. So 5 squared plus negative 12 squared equals r squared. So 25 plus 144 equals r squared. That is 169. And so the square root of 169 plus and minus equals r, just the plus. R is always positive, so r is 13. Keep in mind, though, that we're going to have to pay more and more attention to that plus and minus when I do a square root, because x and y are signed. That could be positive or negative, and I have to choose based on which quadrant our angle is in. This time, it's r. R is always positive. Okay, so we have a 13 up here. All right, so we know the 3 sides of this triangle, so we know all 6 trigonometric ratios. So the sine of beta will be its opposite, 5 over its hypotenuse, 13. The cosine of beta is negative 12 over 13. It's adjacent over its hypotenuse. And the tangent of beta will be opposite 5 over adjacent negative 12. Just rewrite it. Don't put a negative in the denominator. So it's negative 5/12. It doesn't matter which number is negative. A fraction is not considered simplified with a negative in the denominator. Then, keeping that in mind, as I flip these into cosecant, this is cosecant, it will be 13/5. Secant beta will be negative 13/12. Again, it doesn't matter where the negative is, just that there is one negative. And so the ratio is negative 13/12. And then the cotangent of beta is negative 12/5. All right. So once I know all 3 values of sides, I can get all 6 trigonometric ratios. And this point here at the bottom, it says the value of a trigonometric function for an angle depends only on the angle. We noted that the first time we defined them, not on the choice of point for the coterminal side. The angle remains the same at any distance. So that particular point didn't have to be at negative 12/5. It could have been any point on that arc, because the ratios would reduce down and be the same, any point on the arc. Okay. In example 3, the terminal side of an angle in standard position lies on the given line in the given quadrant. Find the exact value of the 6 trigonometric functions for this angle. We're going to draw a picture to start. Okay, so first thing is that the line is 4x plus y equals 0, so that is the line y equals negative 4x. So it goes through the origin with a slope of -4. So if I go down 4 over 1, I'm going to have to get some scale to this, but it's going to be a pretty steep decreasing line. Okay, and we're in quadrant 2, so we're actually not going to be using the negative quadrant. We're going to be using this quadrant, okay? And so just want to arc over here, okay? Doesn't matter what point I use at all. I can pick any point in that quadrant. So let's pick, for example, if I went up 4, back 1, this point would be -1, 4. If you plug in -1 for x, you get 4 for y, right? So that point is on this graph. I'm just using slope in it to calculate this. Y-intercept of 0, 0, slope to calculate that point. When I have that point, boom, I have a reference triangle. In this reference triangle, the x value is -1, the y value is 4, and I don't yet know the hypotenuse, but I can calculate it. So I can say -1 squared plus 4 squared equals r squared, or whatever you want to call it, c for hypotenuse, squared. So that's going to be 1 plus 16 equals r squared. So the square root of 17 is our r. Okay? Square root of 17. I'm going to try to squeak that in right here. Square root of 17 for that hypotenuse. So, find the exact values of all 6 trigonometric functions. So I haven't named the angle, so let's name it theta. So we talk about sine of theta, cosine of theta, tangent of theta, and then once we have the primary 3, we'll go into the reciprocal functions. First, sine of theta. Okay, so sine of theta is going to be opposite 4 over hypotenuse. So 4 over square root of 17, or if you rationalize, that's 4 square root of 17 over 17. Cosine of theta is going to be -1 over square root of 17, or if you rationalize, negative square root of 17 over 17. Tangent of theta is going to be opposite over hypotenuse, so that's going to be 4 over, I might have said that out loud wrong, but it's opposite over adjacent is what I meant to say. I think I pointed in the right spots. Opposite over adjacent. So 4 over -1, which of course simplifies to -4. Then we can get the reciprocal functions. We can get the cosecant of theta, the secant of theta, and the cotangent of theta. Instead of recalculating them, we're going to just flip our original ratios. So it's going to be the square root of 17 over 4, negative the square root of 17, no need to write the 1 in the bottom, and then -1/4. And I have all 6 trigonometric ratios.